So this is a run-through of a project for a secondary mathematics class that is utilizing technology and just simple math concepts, so it will help the kids be able to connect mathematical concepts to actual real life things and things that you can actually touch and feel. This is using a 3D printer, and this, like in previous blog entries, is the TAS 6, which is the 3D printer I used in this situation. And basically this is a run through of what the project is going to be, and basically kind of an example of what potentially this project would be. So this specifically would be for a Calc 1 class or for a Pre-Calculus class, depending on how extensive your Calc curriculum goes. And basically it is talking about volume of equations and being able to rotate an equation around an axis to find the volume of it. And then we are actually going to test that volume. This is important for education because a lot of kids they see math as only numbers, and they don't quite understand that math is everywhere, and it's actually just a more accurate way of explaining and testing real life things that you can do kind of simply, but math is just the more accurate version. And so in this project, we'll be focusing on this concept of volume, and this specific formula of volume equals pi of the integral from a to b of a function of, in this case, y squared. And you can do a function of x too. That just depends on what axis you are rotating around. And in this case, we are rotating around the y-axis. And the function we are specifically using is this y equals x squared. So it's a simple parabola. But because it is rotated around the y-axis, we need to actually solve for x instead. And so this is still a parabola, but just in the x equals, not the y equals, so the function of y. Following through, the next step would be to find the bounds of your function. And here's a graph of a simple parabola. It is not accurate, but it's a simple sketch. And in this case, basically, you want to pick the height of whatever you're going to print out. In this example, I decided to use 5 centimeters as the height because it is a simple size that we can all check. And so so basically this height will not change depending on where it is on the plane, but the function would. So in this example, it's a simple y equals x squared, therefore it starts at the origin, so 0. And so these bounds are vertical because we're focusing on y and we're rotating around the y-axis, so these bounds would be the vertical bounds. So we are starting at the origin, so that would still be 0. And then because it's 5 centimeters, it'd be 5 from the origin vertically. So this 5 would be our upper bounds. And so in this larger formula, this A would be your 0, right? And then this B up here would be your 5 because it's your beginning bounds and your upper bounds and your lower bounds. And so now to calculate the volume, this is when the math, just learning that, understanding how to do this will come in handy for this. Will come in handy for the students, and this is the actual mathematical thing that you would normally do on a homework sheet or on a quiz or even a test, right? And so this would be the calculation for it. And in this specific example, right, you plug in your function to the formula and you punch in the numbers, and you get this 39.27 centimeters. This is going to be interesting going forward when we actually test the volume, when we actually print this, when we actually print the shape and then we actually test the volume, because note that this formula has a pi in it, and pi is an irrational number. It goes on forever, so in the real world we can't quite measure and say, oh yeah, that's definitely pi, because it will all be kind of rounded, and that's why everything was rounded here, to get a simple answer. And so now we're going to move on and actually test the volume. This is how we're going to do it for this project. So first of all, you're going to print your model. And this is what it would look like when it's printed. For the most part, you could print it solid or you can print it hollow. To save on time, I printed it hollow. This will just change how you're going to actually test it. And so how we're going to test it is that we are going to have a beaker or a measuring cup or something where we can measure the displacement of water. And this is something kids have learned in science, like in middle school. So by the time they're in calculus or pre-calculus, they should be able to recognize what this is. And basically how it works is, like, we start off with the level of water. We have our shape, and we submerge it and measure the displacement. So specifically, I have this right here, this measuring, and each dash here is 150. And so because I did not currently have access to a beaker, like an actual beaker with all the beautiful notches that are more accurate than this, I had to make do with this beaker and being able to measure it with a ruler. And and when coming across this problem, I just decided to measure the milliliters, and this is currently at 300 milliliters that was measured out and poured into here. And basically I just measured this out with a ruler, and then when I measured the displacement, I measured the displacement of the ruler and created a ratio to actually find the new displacement of the water. But that wouldn't be necessary in a classroom if you can, and you probably would be able to get access to actual beakers and being able to fully test this out. So let's see how you would submerge it. Because, like I said, my thing is hollow, it won't actually sink well. So how this will work is you just submerge it to the brim. This actually changes the accuracy of this test, right? But you can see how it's displaced like this, and then you'd have your partner actually measure it out. I did this beforehand, so you don't necessarily have to see me measuring that, but see how the water is now displaced. You'd measure that with the ruler, or if this was an actual beaker, you'd be able to measure that with the little side hash marks and be able to then calculate the displacement. So like I said, I did this beforehand. The observations of the original water level was 300 milliliters, like I said, and the new one was 340. And so then the students would go on to their calculation, and like you easily learn in science class in like 7th or 8th grade, you learn that you take the new water level minus the old water level, and that gets you your displacement, which therefore gets your volume. So we have 340 minus 300 equals 40 milliliters. So the water was displaced by 40 milliliters, which means the volume of the shape was 40 cubic centimeters. And this milliliters centimeters is something you also learn in science, so that would be a connection from mathematics to science on, the equality between milliliters and cubic centimeters when it comes to volume. And so then they would see this result, and then they would compare it to what they originally got, this 39.27. And from here, you would have, little thinking discussion questions, and this would probably be more like an in-class activity rather than a full-on like project, because it only is utilizing one simple mathematical concept and not multiple. But it would be a very fun hands-on activity for students, so that would actually help them understand what this is and why we do this in math. And so a lot of questions you could ask is like, why isn't it exact, and which answer is actually more accurate? So it's not exact because there are plenty of things that could have gone wrong during this test. Like I said, I didn't actually have a beaker, right? So the measurement could be off there. And this shape wasn't actually it wasn't actually printed solidly. It was only printed hollow. So so there could have been some missed information or missing data. Whatever you print could print incorrectly, and a size could be off, and so that can be taken into consideration. But I think as a math teacher, what I would highlight is that between the two, this one is more accurate because math comparatively to science, and what I would highlight for the students to be able to connect math to other classes is that between observing the world, math is the most accurate, and this is actually not even the most accurate answer. The most accurate answer would be that 12.5 pi would be the most accurate answer of all of this, because, like I said, the shape is circular, and that's why we get pi, and that's why it's not completely accurate, because pi is irrational. And so this would be able to open up the discussion for students to understand the importance of math in the grand scheme of things, be able to understand this concept deeper, because for not only visual learners who can see this, but also kinesthetic learners who can actually touch and feel this shape, be able to test it. So this would actually make the concept easier to grasp for other types of learners and actually get them interested, because they won't be sitting in their seats just taking notes of what this does and like given like example problems. They will actually be able to fully comprehend and fully understand what this is and why we are doing this. Yeah, and so that is, this was done in the UNL Makerspace and the College of Education and Human Sciences. And basically I utilized their 3D printer and I looked and explored the 3D printer to think of how can we make math more accessible to more accessible and understandable to students who don't naturally think mathematically. And I thought that the 3D printer can take these mathematical concepts and allow you to touch and handle and feel them. And so it becomes more accessible and becomes more interesting to students who wouldn't naturally be. And there are plenty of other projects that you can think of for the 3D printer, varying age levels, specifically thinking about with 3D shapes and volume, surface area as well. There are others, but this specifically one with this equation, it just brings it all into the real world, and this is why this is important. This is my thoughts and my project design using a 3D printer for a math class, for an in-class or a project activity. All right, thank you. And I will see you later with more math thoughts and more project ideas.